Hey, you're back with Mrs. Mays. Today we're looking in AP Chemistry at how to distinguish between atoms, isotopes, and molecules. So let's get started. When we're distinguishing between atoms, how do we know that we're looking at two different types of atoms? How is an atom of, say, hydrogen different from an atom of oxygen? You see, elements are different from one another because they contain different numbers of protons. In the nucleus of the atom, the proton, the positive charge, is kind of the thing that gives us the identity of that atom. Everything else can change, but when protons change, you get something new entirely. We call this the atomic number. The atomic number is representing the number of protons in the nucleus of an atom of that element, because that is identifying what type of element that substance is. So if we look at the periodic table, you'll notice a couple of different numbers. One number is a whole number, the other one has decimals typically. The whole number is your atomic number, but every periodic table does it a little bit differently. Sometimes they put that atomic number here, and sometimes they even put it at the bottom, so just use the legend of the periodic table to figure out which number is which. But generally speaking, the whole number is the atomic number, and something with decimals will be the atomic mass. So in this example, how many protons does krypton have? Look at the atomic number. Right, 36 protons. And if the atoms are electrically neutral, all the positives balance all the negatives, then how many electrons does krypton have? Protons have to balance electrons, so that would make 36 electrons as well. Okay, let's move on. So in the nuclei of the atoms, there are protons, but there are also neutrons. The total number of neutrons and protons put together is called the mass number. Protons and neutrons make up the entire mass of the atom. The electrons weigh such a small amount that it's not even measurable when we're looking at the mass number for the atom. So if the atomic number is equal to protons and electrons, then we could determine the number of neutrons in an atom by subtracting mass number minus atomic number. Number of neutrons is mass number minus atomic number, because mass number comes from the sum of protons plus neutrons. So if we subtract away the protons, we are left with the neutrons, right? Piece of cake. So let's try it. If we have the mass number for gold at 197 and the atomic number is 79, how many neutrons are in that nucleus? To solve this, we would subtract 197 minus 79. The mass number is always written on the top and the atomic number written on the bottom. So we subtract these two. So this particular isotope of gold has 118 neutrons. Now I can change the neutrons and it would still be gold. It would just weigh more or less. But if I change the protons, it's not gold anymore. That's what isotopes are all about. The atoms of an element that have the same number of protons and electrons but differing numbers of neutrons are called isotopes. So their protons and electrons can be the same, but when the neutrons are different, they're called isotopes. Their chemical properties are the same because protons and electrons are still even. That's what determines its chemical reactivity, what the electrons are up to. But their mass is going to be significantly different because the neutrons have mass. Let's look at carbon-12 and carbon-14, for instance. Carbon-12 weighs 12 because there are 6 protons and 6 neutrons. Carbon-14 weighs more because there are 6 protons and 8 neutrons. So this weighs 2 more, and 2 out of 12 is about 16%, 17%. Now imagine that tomorrow when you walk into school you weigh 17% more than you do today. Do you think anybody would notice a difference? Probably so. We can tell isotopes apart because they weigh different amounts. Their masses are vastly different, and we can tell the difference in a mass spectrometer especially. So to measure average atomic mass, we have to consider that not all isotopes are average. Not all atoms fit the average weight. So we have to take a weighted average. In other words, we consider not just the mass, but also the relative abundance of the isotopes as they occur in nature. The units that we use are called AMUs, which is short for atomic mass unit. Pretty simple, right? Americans must have named that unit AMU. And to solve for average atomic mass, we're going to follow these steps. Multiply the percent abundance of each isotope times the mass of the isotope, and then find the sum of all the isotopes. It's that easy. Now watch out for percents. You either have to change this to decimal form, or what I like to do is at the end, after I add everything up, I just divide by 100 then, so I'm not moving decimals all around and putting them back, and I just move them at the end. Let me show you what I mean. So first we have the relative abundance of the oxygen 16 isotope, and we'll multiply that by the mass. So get your calculator out and do this multiplication. I'll get mine, you get yours, and then we'll be rolling. So my percent for oxygen is 99.759 multiplied by 15.995. Now we're going to add to that the next one down, 0.037% times its mass of 16.995. And then add the next one, 0.024% times the mass of 17.99. So not a whole lot of isotopes of oxygen are going to weigh 18, just a very tiny proportion. Most of them weigh 16. I expect the average then to be a lot closer to 16. And look what number did I get? 1500. Oh my gosh. Remember I said we have to change that decimal or percent to a decimal sometime? Well, now is the time when we're going to do it. So 15.967, and I get to keep, let's see, 2 sig figs it looks like. So let's keep 2 sig figs. That would give us an atomic mass of 16 AMUs for oxygen. So look at your periodic table. Does that seem right to you? Let's look at our periodic table. Do we have oxygen says 15.999, and we said 16. So hey, we are good. Okay, now I want you to give it a try. If uranium has 3 common isotopes, where 234 is 0.01%, 235 is 0.71%, and 238 is 99.28%, then when you do the average atomic mass of uranium, you had better get something that's a lot closer to 238 than 234, right? Because it has the most abundance. Give it a try, work it out. I'm going to check in class to see what answer you got. Let me show you another technique. Some other kind of data you might see is that we'll use mass spectroscopy to generate this graph of the relative abundance. So here's the mass spectrum of neon, and we see, comparatively speaking, the tallest line is at 20 AMUs. So 90.5% of the atoms of neon weigh 20 AMUs, and only 0.3% weigh 21. And then 9.2% of the neon atoms weighed 22. So what do you think? Is the average going to be closer to 20 or 21 or 22? Make a guess. What's your logical guess? Let's find out. 90.5 times 20 plus 0.3 times 21 plus 9.2 times 22. All right, check to make sure we did our math correctly, and we get 20. Oh, yeah, divide by 100. I just moved the decimal in my head without saying what I was doing. Sorry. So my average atomic mass came out to 20.187 AMUs, and looks like, I don't know, sig figs are hard to tell given this data to know what's really meant, but somewhere around 20, and we said 20 should have more, right? So it should be closer to 20. Let's look at the periodic table and see what it says. 20.18. Hey, just like we calculated. All right, now let's just review from regular chemistry, general chemistry. Let's review what we learned before, predicting numbers of protons, neutrons, and electrons. This may seem super easy, but on the other hand, maybe you need a refresher. So let's count up for tellurium, or the ion telluride, how many protons are in this atom. We look at this bottom number, and we see the protons are 52. Now I'm going to skip down to electrons because that's the next easiest thing to do. Protons are normally equal to electrons, but this 2 negative charge tells me I have 2 more electrons than normal because I have 2 negative charges, and negative charges come from electrons. So I'm going to call this electrons 54 instead of 52. And now for the neutrons, we take the mass number minus the atomic number, and we get 76 neutrons in that particular isotope of telluride ions. Now let's look at uranium-238. So for protons, we look at the bottom number, 92. That's our atomic number. Neutrons, subtract 238 minus 92, and what is that? 146 neutrons. And electrons, look, there's no charge here, so electrons must be balancing the protons because all the charge is neutral. Now our last one we'll do in the podcast is tin-4. Tin-4, good buddy. I know that was lame, but I had to do it. I was compelled to. The protons are 50, that's the atomic number. For neutrons, 120 minus 50 is 70. And then electrons, the negative charges, oh gosh, now we have a positively charged particle. So that means that when I started with 50 electrons, now I have protons outnumbering electrons. So subtract my electrons away because I lost 4 electrons, lost 4 negatives, that gives me 46 electrons. So atomic number minus charge, if you're careful with signs, will give you the number of electrons. Got it? Good, because now it's your turn. You have 3 of these to do so that you can show me in class that you get it, because I want to make sure that this is not going to hold you back in EP chemistry. All right, last thing. What if we don't have an element? What if we have a compound? How could we tell the difference between molecules? Molecular formulas are used to tell how many atoms of each element are present in a compound. So you might have CH4, or you could have C2H6, or you could have any variety of these combinations, N2O5, NO2, NO. And we want to know how many of each thing are present, because these atoms will just combine in ways that cannot be determined by the crisscross method of crossing the charges. We just have to look at their structural formula to decide what kind of thing we're dealing with. Sometimes, by the way, this is called a molecular formula. And what we know is when they combine, they're going to combine so that all the atoms satisfy the octet rule. Generally speaking, atoms tend to attain the electron configuration for noble gas by sharing electrons. So however we put them together, everyone needs to have 8 electrons around it to be considered stable, except for hydrogen that only has 2. So for molecules, what you'll find is atoms of different elements combine according to the octet rule. And that's it for atoms, isotopes, and molecules. See y'all next time.